When you think of water, what comes to mind? Is it the water flowing from the faucet? Or the stream you passed on a drive? Maybe a lake or reservoir from a recent hike? These visible sources often come to mind first, but nearly 98% of the world's usable freshwater is actually groundwater. Water stored in the tiny spaces within soil, sand, and rock beneath our feet. These underground storehouses, called aquifers, are essential to our water supply. There are 68 major aquifers in the United States that support agriculture, cities, and ecosystems. The High Plains Aquifer helps produce 40% of the nation's wheat, while California's Central Valley, known as America's breadbasket, relies on groundwater for over 250 crops. Millions of people depend on groundwater for drinking water, yet coastal aquifers are at risk of seawater intrusion, and industries like AI-driven data centers increasingly rely on groundwater for cooling. Even endangered species, like Florida's manatees, depend on groundwater-fed springs for their survival. But groundwater is running out. Over half of the nation's wells are in decline, with agricultural, coastal, and arid regions experiencing dangerous overdraft. To help restore groundwater supplies, many communities are using Managed Aquifer Recharge, a technique that intentionally directs excess surface water underground to replenish aquifers. One major challenge in expanding MAR is ensuring enough clean source water. That's where I, a hydrology graduate student at UC Davis, come in. I study where river water can be captured and conveyed underground to help rebound rapidly declining groundwater supplies. My research shows that floodwaters in key aquifers, such as the Central Valley, Texas Gulf, and Mississippi embayment, could be redirected onto floodplains, farmland, and bypasses, where water can naturally infiltrate and recharge groundwater. Beyond finding source water, there are physical, legal, and environmental barriers to expanding MAR. The timing, duration, and seasonality of flood events impact how much water can be captured. Water rights and environmental protections must also be considered to protect important stream functions like sedimentation and migration cues for native fish. Additionally, researchers in my lab study how flooding large areas of land could leach natural and human-derived contaminants like arsenic or nitrate, into groundwater. Despite these challenges, MAR offers a powerful tool for securing water supplies. If implemented carefully, it can help restore depleted aquifers, protect drinking water, and build resilience against drought. By refining our understanding of groundwater recharge, we can scale up MAR safely and effectively. Groundwater might be out of sight, but it should never be out of mind.